In this video I'm going to talk you through question 1 of the 2015 C3L6 challenge. Now you can find the papers online, the link's going to be in the description of the video, and I seriously recommend that you have a go at this paper before listening to this video, because otherwise I'm going to ruin the answers for you and you're not going to get as much out of it. So if you haven't had a look at the paper yet, then go away now, have a go at it and come back to watch the video afterwards. You'll know that you're given a periodic table in this paper, so make sure when you need to use relative molecular masses, you calculate them from the relative atomic masses given in this table. And you're also given the Avogadro constant. Make sure you use this value, which is given to 4 significant figures here. Don't just use a more rounded value that you might have memorized. Okay, so in this question you're actually given a lot of background and you might think this is completely irrelevant information, but do make sure you just scan it because it does sometimes contain important information. For example here, between parts A and B, it gives you the definition of what isoelectronic means, which you might be familiar with but you might not. So do make sure you read the information between parts as well as the information in the actual parts of the question. So now we're going to move on to part A of this question. Here we need to write down some chemical equations for thermal decomposition reactions. So we know that each of these processes is giving off oxygen. It's telling us that in the question. But we do need to work out what other products are formed. Sometimes actually it's giving us the answer. Here it says the product contains the nitrate 3 ion. So we need to work with what we're given and with what we know could possibly be formed. So first of all, we need to work out what the formula of mercury 2 oxide is in order to be able to write down this first equation. So if mercury has got an oxidation state of 2, oxygen also has an oxidation state of 2, well minus 2. So the formula for mercury 2 oxide will just be HgO. Now we know that it's going to be decomposing, so there's no other reagent present. And we know that one of the products is going to be oxygen. Now there's a number of ways of making this work, but in order to balance the equation, if we've put an oxygen molecule on the right hand side, we want to have 2 HgO molecules on the left hand side. Now, other than oxygen, what could the other product be? Well, one of the most obvious options here is of course 2Hg, mercury as just the element. And now we've got a balanced equation, 2HgO giving 2Hg plus O2. The question doesn't just ask for the equation, it also asks us to underline which element has been reduced in the process. Now this is a really easy part to miss. Don't forget, if there's 2 parts to a question, make sure that you do both the parts of the question. Now in this case, the oxidation state of oxygen is going from minus 2 to 0 in the element. The oxidation state of mercury is going from plus 2 in HgO to 0 again for the element Hg. So the reduction is taking place for the mercury because the oxidation state is going down from 2 to 0. The second compound here is silver 1 carbonate. So once again, we need to start by working out the formula of the compound. So we know that the carbonate ion is CO3 2 minus, hopefully you know that. And a silver 1 ion is just Ag plus. So in order for the 2 minus charge to balance out with the positive silver ion charge, we need 2 of the silver ions. So that means that our formula is going to be Ag2CO3. Now we know once again that one of the other products is going to be O2, so we can write that down. And we're going to think about what the other products might be here. So even thinking back to GCSE, you will have encountered the decomposition of some carbonates. In that case here we're getting metal oxides and carbon dioxides out. You will have seen this for calcium carbonate, for example. Now you might think here then that we're going to get CO2 as one of the other products. So if we write down CO2, now in order for this to balance, we do still need to get silver out as well. And note that the oxygens aren't currently balanced. So what are we going to do about that? We're going to probably want to have 2 silver, 2 CO3. So now we need 2 silvers on this side. Now we need 2 CO2s on this side, and now it looks like we're all balanced. We've got 6 oxygens, 2 silvers and 2 carbons on both sides. Now again, let's not forget the other part of this question, which is identifying the element that's been reduced. So once again, it's going to be the metal, which is going from +1 in the carbonate to 0 in its elemental state. So the silver is being reduced from +1 to 0. This next part is in a sense a bit easier because we're actually told what the products are, but we do need to work out what nitrate 5 and nitrate 3 mean in a formula. Hopefully you know how to do this, because the number in Roman numerals and brackets, once again, it just means the oxidation state as it did for the metal earlier. So in this case, nitrogen goes from having an oxidation state of 5 to having an oxidation state of 3, which really answers the part about which element is reduced. And a nitrate 5 ion has a formula of NO3 minus. That works out because 3 times -2 for the oxygen gives us -6, plus 5 gives us -1, which is the charge on the NO3 minus ion. Now the charge on the potassium ion is just +1, so the formula of potassium nitrate 5 is just KNO3. Now the products here are once again oxygen, as in all of these parts, and we're told the other product, well, at least one of the other products, is the nitrate 3 ion. So the nitrate 3 ion, the oxidation state of nitrogen is +3. In order to get an overall -1 charge, we need -4. We get that from 2 oxygens, because oxygen is an oxidation state of -2. So that means that the formula is NO2 minus. And remember, we've still got our potassium plus ion, so we've got KNO2 coming out there. Now this equation is clearly not balanced, so we're going to have to do some multiplying out again. And if we just add a 2 here and a 2 here, we've now got 6 oxygens, 2 potassiums, 2 nitrogens, so everything checks out. And I know that we answered this part earlier, but remember to again underline the element that's being reduced. So in this case it's not a metal, it's the nitrogen. The potassium stays as +1, but the nitrogen is reduced from +5 to +3. Final part of this part A is a bit more complicated because we've actually got 2 things reacting together, and they once again have to produce oxygen, but we need to work out what the other products are. So it's an acid and a metal oxide reacting here, concentrated sulfuric acid and manganese 4 oxide. Most acid metal oxide reactions you've met before will have produced a salt and water. Remember, that's one of the standard equations that you've probably come across. So we're going to assume that the products here are going to be a salt, water and just oxygen in addition to those as well. So let's start by putting down the formulae again. So concentrated sulfuric acid, hopefully no H2SO4 for sulfuric acid, and manganese 4 oxide. So here manganese has an oxidation state of 4. In order to balance that with oxygens -2, we need 2 of the oxygens. And then the product, as we said, will be water, oxygen, and as for the salt, we need to think about what we are left with. So we've still got the SO4 2- ion hanging over here, and we've also got a manganese ion. Now originally we had a manganese in oxidation state 4. In order for us to generate this oxygen, we have been oxidizing the O in this MnO2- to O2, because it went from oxidation state -2 to oxidation state 0. So something has to get reduced. It's not anything in the water. It has to be the manganese. So in fact we're going to be generating manganese 2 ions instead, and we're going to end up with MnSO4. Now don't worry too much if you didn't end up with this formula, because anything that seems sensible and that follows the rules of chemistry will be awarded answers in exams like this. So for example, if in the second equation you had generated carbon monoxide rather than carbon dioxide, that would have been entirely accepted. Now what we can't forget to do, of course, is balance this equation. And if you add up the oxygens, you realize you have 6 on the left-hand side, but 7 on the right-hand side. Now you can in fact balance this just by putting a half in front of the O2 if you like. Or if that's not something that you're familiar with, let's get rid of this. You can just multiply everything else by 2 instead. All the other elements are balanced, so we're all good, but we need to remember to indicate which element has been reduced, and as we said, that's manganese, which goes from +4 to +2 in this. On to part B now, where we need to draw the dot and cross diagrams of a number of species that are isoelectronic with the nitrate ion NO3-. We were told what isoelectronic means in the question, so hopefully you are happy with that. We also need to give the formula, so let's not forget to answer all parts of the question as before. It asks for the formula as well as the dot and cross diagrams. So in fact, let's start with the formula, because I think that's a bit easier, and it'll help us answer the dot and cross diagram part as well. About carbon in relation to nitrogen, you know that it's in the group before, so it has 1 fewer electron than nitrogen. So in order for the species with carbon as the central element to be isoelectronic with the nitrate ion, we need to have 1 additional electron. So instead of having NO3- with the 1 additional electron, we will have CO3 2-, because we now need 2 additional electrons. Moving on to boron. Boron is 1 group further to the left compared to carbon, so it's going to be the same kind of shift again. We need to add 1 more additional electron because the central atom can provide only 1 fewer now. So the formula is going to be BO3 3-. In this case, we need 3 additional electrons. Looking at oxygen, it's kind of the opposite scenario. So oxygen is in the group to the right of nitrogen, so it's got 1 extra electron. So instead of needing that additional electron that we have in NO3-, we will just have that electron provided by the oxygen in the middle. So the formula is going to be neutral O4, because we no longer have any additional electrons present. Now for drawing these out, so we're told that isoelectronic means that the electrons are arranged in much the same way as they are in the original ion. So for our CO3 2- ion, we're just going to start off with the same kind of general arrangement. Now what is going to change is that instead of having 5 electrons provided by the central atom, we've only got 4. So we start by allocating them evenly here, and then ending up with 2, for example, here, as this was done for the original nitrogen compound. Now we do need to form a proper covalent bond over here, and we need to form a double bond over here in order to be isoelectronic with the way it was drawn earlier in the nitrate ion. So we're going to have to fill that in with oxygen electrons. So let's form the bonds over here, and let's form the bond over here. Okay, now the carbon has a full octet. As expected, we need to fill in the additional electrons for oxygen. Now remember, this oxygen up here, it's used an extra electron compared to the nitrogen, so that's where the additional electron is going to be needed. And the rest will just look exactly as it does in the nitrate compound, because we haven't actually changed the electron arrangement over there. It's worth bearing in mind that it doesn't actually matter too much where you put the additional electron, as long as the numbers all match up, because it does depend on how you produce these compounds, where they would be coming from. So don't worry too much about where you place the additional electrons in the structure you draw. Now for boron, it's much the same story, except now we've only got 3 electrons provided by the central atom. That means that the other bonding electrons will have to be filled in by oxygen again, so we're going to lose some lone pairs and going to fill in some additional bonding electrons provided by oxygen. Okay, so if we start off by drawing out this general scheme again, now let's just give each of these bonds one electron from the boron, and then we need to fill in the rest with oxygen electrons, or additional electrons if you like, it doesn't really matter. Now we need to be slightly careful about our lone pairs now. So again, we've got two lone pairs on here, but in order to make it work, we now need an additional electron here, and we have got 3 lone pairs here for oxygen to have a full octet. 1, 2, 3, 4, 5, 6, 7, and then there's an additional electron there. And finally we're going to place the final additional electron on this other oxygen out here, where we had it earlier as well. Again, as I said before, don't worry too much about where you place these additional electrons, it doesn't really matter too much, as long as all the elements have got full octets as expected, and the electrons provided by individual atoms match as expected as well. Okay, the final compound here is the oxygen O4. So as we said, there's no additional electrons present here. All the electrons are provided by oxygen, but obviously we want to distinguish the oxygen in the middle from the other ones. So the oxygen in the middle is going to provide 6 electrons, just like the other ones, but we're going to, if we allocate them evenly, we would end up with these dative bonds everywhere. And then to make this work, we'll need a pair of electrons provided by one of the outer oxygens over here, similar to what we had earlier, and we've got 2 lone pairs on that oxygen, and the other oxygens have got 3 lone pairs, all in this case being their own electrons. No additional electrons present. Okay. Moving on to part C, perhaps the most difficult part of this question is reading it properly, because we've just been working on the nitrate 5 ion, but we've now moved to talk about the nitrate 3 ion. So make sure you do answer this question for nitrate 3. The nitrate 3 ion, as we discussed earlier, is NO2-. So we worked that out using the oxidation state. Hopefully you remember that from part A. Now we need to find a compound which is neutral but is isoelectronic with NO2-. So we can use a similar strategy to what we had in part B. If we move a group along, then we suddenly have an element that has that additional electron already. So if we substitute the nitrogen for an oxygen, we no longer need an additional electron, but we retain the same number of electrons, just because oxygen has an additional electron compared to nitrogen. So that will give us O3. Now it also asks for the name of the compound, and hopefully you know that O3 is called ozone. There are other ways of making this work, and you can come up with other neutral species isoelectronic with nitrate 3. However, you'll probably struggle to find another one that has a simple name that you know. Okay, we now move to part D. There's a lot of data in this, particularly above the part that's actually annotated as D. And we need to make sure that we are calculating the right thing. It's generally quite useful to draw a diagram in question like this. So if we know that the lowest energy that we're going to have in any of these scenarios is going to be the energy of the elements. So that's just going to be O2, in fact 2 times O2 in this case, but let's not worry too much about that. We can then have different forms of O4, and the ones that are discussed here is the Packard ring form and the pinwheel form. We're told that the planar structure has been calculated to be 89.3 kilojoules per mole, higher in energy than the Packard ring. So this is the planar structure, and it's higher in energy than the Packard ring form. So if we put on our diagram the 2 other energies that we have, this doesn't have to be to scale at all. In fact, you don't know what the numbers are yet. This is just for your own benefit. And if we can add on an energy axis as well, this is increasing enthalpy. Okay, so we now know that the pocket ring structure is lower in energy than the pinwheel, linear pinwheel. And let's put on the numbers that we're given in the question. So the planar structure is 89.3 kilojoules per mole higher, so this difference here is 89.3 kilojoules per mole. We're also told that the standard enthalpy of formation of the pinwheel is 480 kilojoules per mole. Now remember, the standard enthalpy of formation is this energy going down to the elements. So we know that this is 480.0 kilojoules per mole. And lastly, we're given that the activation energy for the dissociation of the pocket ring 04 into 202 is 48.7 kilojoules per mole. Now the activation energy is going to be the energy between the pocket state and the transition state over here, so this is 48.7 kilojoules per mole. And we're asked to work out the activation energy to form the pocket ring from O2, so that's going to be the energy going to the same transition state but up from the elements over here. So that's the value we're looking for. And now it's relatively easy to see which way around we need to do the calculation. So we need to add this, then subtract this value, and then add this value in order to cover EA, the quantity that we're looking for. So if we write that out, we've got 480 minus 89.3 plus 48.7, all in kilojoules per mole, which gives us the final answer of 439.4 kilojoules per mole. So hopefully it was easy to follow there why we had to subtract one of the values and add together the other ones. And it's usually very helpful to draw out a diagram like this in similar questions. In part E, it's important that we don't get stuck and read the procedure that's been carried out here over and over again. It's quite complicated what's going on, but we need to just focus on this mass spectrum. So we can see that there are 3 peaks, and we know that they result overall from this ion over here breaking down. So first of all, let's add up the masses in 1602 and 1802. That gives us 32 plus 36, which is 68. So we see already that corresponds to peak C over here quite nicely. So that tells us that C is 1602, 1802 plus. Let's write that down straight away. And now we can think about what the other 2 ions can be over here, A and B. So A is at 32, we notice. Now we can get 32 by adding 16 and 16, so we're going to say that A is going to be 1602 plus. And we can get 36, which is what peak B is, by adding 18 and 18, so that tells us B is 1802 plus. What's a bit unusual is that we don't see a molecule between A and B. The reason we might expect to see one is that we can of course have a diatomic oxygen molecule which contains 1 atom of 16O and 1 atom of 18O, which would give it a mass of 34, and the peak should be somewhere here. But we don't see one, and that's important information for the next part of the question. So as I've just mentioned, we'll need to use the information that we didn't get isotopic mixing. What I mean by that is that we started off with a 16O2 and an 18O2 molecule to form this O4 shape. It then broke down again to give a 16O2 plus and an 18O2 plus in the mass spectrum. It didn't give us a 16O, 18O molecule. That tells us that we don't get a molecule, an O4 molecule, which has equal bonds. So if we had this square shape, for example, if 2 of these atoms, so for example this one and this one, are 16O and the other ones are 18O, it's equally easy to break the molecule down like this or like this. So we'd expect to see both the original 16O2, 18O2, but also 16, 18O isomers well, isotopomers I should really say. So an isomer is a different type of atom depending on how many neutrons are in the nucleus. An isotopomer is the equivalent for molecules. So if you have different isotopes of the same atom present, but the molecular formula is the same, but also the structural formula is the same, then we talk about isotopes. So which of these shapes are going to be possible? Well, let's exclude a few more. So we said it can't be the square because we would definitely get the isotopic mixing there. For the same reason it can't be this puckered ring because it's also got 4 equivalent bonds. If you look at this pinwheel, now while it doesn't have 4 equivalent bonds, it's got 3 equivalent bonds. We probably wouldn't actually expect to see 2 diatomic oxygen plus molecules in the mass spectrum for this molecule, because it would probably fragment along one of these bonds and we'd see an O3 plus and an O plus in the first place. Yes, it could fragment further, of course, to give O2 plus, but we didn't see those peaks in the spectrum earlier. The other thing to note though is that whatever is in the middle here would be in the bigger fragment in the first place, and it would be in the O2 plus fragment that would form eventually, but it would be equally likely to include any of these atoms on the end, which are, of course, one of them is going to be the same isotope as the one in the middle, and 2 of the others are going to be the other isotope, so we would still get isotopic mixing here. The other 3 shapes are consistent with what we see because we've got different types of bonds. In the rectangular example, it's probably much more likely that we get fragmentation along these long, weak bonds than along these short, stronger bonds. So if this is 16O and 16O, this is 18O, 18O, we'll end up with 16O2 plus and 18O2 plus, but not 16O, 18O, because we're not going to fragment along there. Similarly, in the cis and the trans chain, it's probably far easier to break this middle bond there, which is weaker, and if this is the 16O and 16O, we're going to retain that, and 18O, 18O here, and we're not going to get mixing and forming a 16O, 18O molecule. Now note I labelled that one 16, that one 16, and the other one's 18. Obviously it could be the other way around, it doesn't really matter. But what's important is that we don't get mixing and forming of a molecule like this, because it's far easier to break that middle bond. So the answers we're going to tick here are the cis chain, the rectangular form, and the trans chain. So we've reached the final part of this question now, G, which turns out to be a calculation, and one that isn't structured for you, and it's quite easy to get discouraged when you see so many numbers and it's not really easy to see where to start. The way I like to start questions like this off is by writing out everything I'm given and writing down formulae which I think might be useful in solving the problem. I've now got my energy written out, so I'm given the energy of the particle. It's been accelerated to 4 kiloelectron volts. It's the only type of energy present here, it's kinetic energy, and the relevant formula for kinetic energy is actually given to me in the question, half mv squared. I write it out again here. Now, obviously if there were different types of energy present, I'd need to use subscripts and differentiating between them, but there's only one type of energy, so I can just use E. There's only one mass I have here, it's the mass of the 18O4 molecule. Now it's important to note that because we're working out the mass of an 18O4 molecule, we're not going to use the relative atomic mass of oxygen here. We're going to use 18 grams per mole as the mass of each of the oxygen atoms in that molecule. So the mass of the molecule is 4 times 18 grams per mole, but to work out the mass of an individual molecule we then need to divide by Avogadro's constant. That is because Avogadro's constant tells us how many molecules there are in a mole, and 4 times 18 is the mass that a mole of 18O4 molecules would have, so if we divide by Avogadro's constant we get the mass of one individual molecule. Now you'll note that I've converted all the quantities into SI units. So I've changed the energy into joules, and I've made sure the mass is in kilogram. Notice the base unit of mass is the kilogram, not the gram. And that's important if we want to make sure that everything is consistent in the end, because the joule is in fact a Newton meter, which is a kilogram times square meter per square second. So that means that if we don't have our mass in kilograms, we're going to be off by a few orders of magnitude. Similarly, I've converted the distance, which was given as 10 centimeters, into meters, so everything should be cancelling unit-wise in the end, assuming we use the right formulae. So we've got the kinetic energy formula, as I've said. We also, because we're working out the time that it would travel this path, we're probably going to need to use a sort of rearrangement of the velocity formula, so that's just distance travelled divided by time. Hopefully you are familiar with that formula. It turns out that in this case, once we've written out all the formulae, it's really relatively straightforward to see where we need to go from now. So if we know that the energy is equal to this value, we also have the formula which, given we know the energy and the mass, allows us to work out the velocity. So we just need to rearrange for velocity. It becomes square root 2e over m, and we can then plug in the numbers and all the units will cancel except we're left with meters per second, which is what we expect for a speed anyway. So that's all good. If we look at the time that we're actually asked to work out, we then need to use the velocity formula. We'll rearrange for time, so that gives us distance travelled divided by velocity. And if we now plug in the values that we have, both the one we've worked out for the velocity and the value that we were given for the distance, we get a time of 9.66 times 10 to the minus 7 seconds. That's the units we were asked for it for, so we've now finished the question. Just a quick note on significant figures. You'll note that when I was writing out the numbers earlier, I put some values in brackets. Now I'm actually using that notation to remind myself that even though I'm putting those digits there because I don't want to lose the significance partway through a calculation, I don't actually know these values for significant figures because I'm plugging in 4.00 kilo electron volts. And in this case I'm using 18 grams per mole, which isn't quite exact, so I don't have the significance to more than 3 significant figures in the end. I need to round my answer to 3 significant figures, but I'm going to keep 4 significant figures at least going through the calculation. Ideally, of course, you'll have a memory function on your calculator so you can keep the full numbers right until the very end, well, full to the extent that your calculator rounds it, and then only round the answer to an appropriate number of significant figures at the very end. So that's the end of question 1. I've just included the slide that was in the original question paper, which is some references to where the questions came from, what they were inspired by, so you can check those out if you like. So hopefully this was helpful as a guide to question 1. Question 2 will be covered in a separate video, so bye for now.